Good morning. We were discussing the torsion. After washing the cloth, to squeeze out water before drying, because most of the water has to be squeezed out. Then only the little amount of wetness will be dried. Otherwise, it will take a long time, especially during the rainy season or when the sun is not shining that much and it's cloudy. So, in maximum, you accept pressure by which the water is squeezed out by applying an angular torque on both ends of the cloth, which is bundled. Equal and opposite torque is applied. The planes are subjected to shear. That shear force expels the water out or squeezes the water out. This is a typical example of torsion. So, compressive strength, tensile strength, shear strength, torsional strength. Torsion strength is ultimately nothing but a shear strength. So, shear strength is due to linear forces. Shear stress is due to linear forces, longitudinal forces, whereas torsional stress is due to angular forces or coupled for a moment. Then there is a very important stress developed in addition to the direct stress. Wherever you have a direct stress and if the loading is not symmetrical, loading symmetrical means the load has to act along the axis of the material, of the component of the element. When the load is axial, it will be subjected to direct stress. Whenever the load is along the axis, that material will be subjected only to the direct stress. And the nature of stress will be either compressive or tension according to the push or the pull. But if the line, any load or any force will have a line of action. To define a force, you need its quantity of the force, the quality of the force, the point of application of the force, the sense of the force, and the line of action of the force. These are the requirements. How much quantity, the magnitude of the force. Force is a vector quantity. So, its sense or direction, the point of application, the quality, whether it is a linear force, whether it's a coupled, whether it's a torque, whether it's a moment. These are the various external disturbances. External disturbance can come as a compressive force or a tensile force, a push or a pull, or it can be a moment or a couple, or it can be a torque. So each force will have a line of action. The line of action of the force coincides with the axis of the material of the component, then it is subjected to direct stress. Line of action of the force falls in the axis. That's the best symmetrical case. If you see all ancient buildings, traditional structures, care has been taken considerably because at that time the complicated designs and the design philosophy, people were knowing how to do it, but they were unaware of why it is done. They are very much conversant in how to do it and how to make the structure stable, strong, and durable. But why you do that? Only in the later period of technology and engineering development, people could understand. Everything was that. How and why are the two things, two wings for engineering and technology. If you know fully about how and about why, then the practice will be very easy. So, symmetrical structures was a slogan in the ancient period, in vernacular architecture, in traditional architecture, in historical monuments. You can see symmetry. Any architecture you take, there will be symmetry by which The line of action of the load and the axis as far as possible will coincide. If there is a shift, even though the shift is very small, that is the line of action of the force and the axis have a shift. That shift is called the eccentricity, small e. Eccentricity. That eccentricity provides a lever arm to the force. That eccentricity provides a lever arm force. So this lever arm will try to rotate the material. Will try to rotate the material. So either this material will rotate, or if there is a resistance for the rotation, the material will deform or bend. The material will deform or bend, resulting in a stress known as bending stress or bending strength. Compressive strength, tensile strength, shear strength, torsional strength. Next is the bending strength. This bending strength is either compressive or tensile. There is no bending strength. There is no bending pattern. There will be a bending phenomenon. But the nature of stress developed on the material will be either compression or tension according to the line of action with respect to the axis. According to the nature of the force. If it's a pull, the nature of bending strength will be either compression or tensile strength. If it is push, the nature of bending strength will be either compressive or tension. Some part of the material. So some part of the material, it will be having tensile stresses developed. Some other part of the material, compressive stress will be developed. And there will be some part, some layer where no stress will be developed. So that layer where no stress is developed is called the neutral layer or neutral axis. Neutral layer or neutral fiber or neutral axis. Neutral axis is that axis where the bending stress will be zero. And the direct bending stress is a direct stress. On one side of the neutral axis, if it is compression, the other side of the neutral axis, it will be tension. Then only you can have a point zero. If everything is compression and everything is tension, it will not cross the 0 point. Because one is positive, another is negative. For our analysis purpose, the tensile stress value is taken as positive and compressive stress value is taken as negative. Compressive stress is taken as negative and tensile stress is taken as positive. Now coming again back to the chair. So the legs of the chair, I told you first, they are subjected to compressive strength. But if I am not sitting symmetrically, if I just take some position like this, I having a line of action of force, and the chair was having an axis. I was sitting like this means the axis and the line of action of the force were coinciding. So the chairs are subjected, the four legs, even though their axes are different, four legs are there. They have an axis, local axis. Each member of the chair is having an axis. So the whole chair is having a center of gravity. Usually axis is passing through the center of gravity, centroid. So that axis is, the global axis is different from the local axis, but fortunately it is symmetrical because all the four legs are equally spaced from the global axis. So that's a symmetrical loading. That is a symmetrical loading. But if I shift like this, the front two legs, because I am shifting towards the front, so the front two legs will be subjected to more stress compared to the back. The back stresses will be little released because the load, the intensity of the load is more near the front legs. So there will be additional stress developed on the front legs compared to the back legs. That additional stress is called the bending stress. That additional stress is called the bending stress. So that bending stress will be compressive in nature for the front legs. For the front legs, that bending stress will be compressive in nature, and for the back legs, it will be tensile in nature. Then only there will be a reduction in stress, because compressive stresses are same. Compressive stresses on all the four legs are the same. Now, when I shift towards the front, if we expect more stress on the front legs, there should be some reduction in stress on the back legs. That is happening only because the tensile stresses are developed on the back legs, back two legs, and the compressive stress is developed on the front two legs. So ultimately, the front two legs will be symmetrically loaded even now, because I am shifting only in one plane. Suppose I shift in this way towards this side, then the action is different. Then these two and these two will come with one front and one back, one front and one back. That is another plane. Now let us not think about it. Now only I have shifted front. So these two legs will be subjected to more compressive strength compared to the rear or the back two legs. So the stress in the back two legs will be direct compressive strength minus the bending strength, because that is tension. Compression we are taken as positive. I mean, compression if you take minus, then minus compressive strength plus. Anyway, it is the difference. Algebraic sum. So it is the difference, numerical difference. Here it is a numerical sum. Compressive strength, bending strength also is compressive, direct stress also compressive. In the rear or the back case, bending strength is negative, the tensile, and the direct strength is compressive. So the legs now are having different values of strength. Fortunately, at least two of them are having the same value. But if I shift in the front and if I shift to the sides, or if I just go towards a corner, all the force will be subject to unsymmetrical load. Very often you see plastic chairs break because this asymmetrical loading they would not have designed. The chair would not have been designed to that much complicated, because the quality of the material and the section of the material should be in such a way that it can stand any eventuality. A building has to stand for earthquake, heavy wind, storms, cyclones, for everything. Sinking, even for sinking, buildings has to be thought of. Standing. So, a general case of loading is totally unsymmetrical. In actual practice, loading will be unsymmetrical. We told the trees will start growing with symmetrical loading in mind. But because of the other eventuality, other requirements of the tree, sometimes there will be unsymmetrical loading too. Because the branches cannot go as they plan. There will be obstruction with other trees from the neighborhood of the growing tree. So the branch will take other parts, by which some unsymmetrical loading will come along with the loading along the axis. So all branches will induce not only a direct stress on the stem, but a bending stress too. So a branch will induce a direct stress and a bending stress. So the legs of the chair have to be designed for direct stress, bending stress. That is the case with buildings also. When you know the fashion of loading, their nature, their quantity, quality, point of application, line of action, the most worst case. In spirituality, you have positive thinking. But in engineering design, we should have, I should not say that it's negative thinking, but as a precautionary measure, we should always think that there can be an unexpected event even after taking into account all external forces. We have to expect the unexpected. So even if you take all precautions while designing a bridge, even then you should think that there's a slight chance of the bridge failing. Then only ultimately our design will be as perfect as possible. Thank you. God bless.